lecture, we will see what is a complement of a set. Let us say we have a universal set U. Let's say universal set U is equal to 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let us say there are three sets A, B, and C. They are all subsets of this universal set. Let us say set A is 1, 5, 7. Let us say set B is 2, 9, 3, 7, 4. Let us say set C is, let us say set C is 7, 6, 3, 2, 8, 5. So these are the three subsets of universal set U. That is given 1, 2, 3 up to 9. Then the complement of any these subsets. Then the complement is defined for any these subsets. Let's say I will define complement for A. So I will say the complement of A bar, that is called a complement of A. It is represented by A bar. It is equal to universal set minus A. If we find this set, it will be, so we have to take all the elements of U and we have to subtract the elements of A. We know the A has 1, 5, 7 elements and universal set has 1, 2, 3, 4 up to 9. So we'll subtract 1, 5, 7 from that and we'll get the A complement. So then A complement will be, so the A complement will be equal to, we have to subtract 1, 5, 7. So we'll get, we are remaining then with 2, 3, 4, 6, 8, 9. So this will be the complement of A. Let us find B complement. So B complement similarly will be, it will be universal set minus B. So if I just see B, it's 2, 9, 3, 7, 4. If we just subtract these elements, 1, we have to subtract 2, we have to subtract 9, we have to subtract 3, we have to subtract 7, and we have to subtract 4 from universal set. So it means then B complement, it will be equal to, we are left with 1, 5, 6, 8. So this will be the B complement. Similarly, we can find C complement or any other complement of a subset of the given universal set. So this is about the complement. Let us see now the properties of the complement of set. What are the properties of complement of a set? Now let's look on properties of complement of a set. If we have any set A, then its union with A complement is equal to universal set. Let us see it here. It's the first property. So let us say it's A, set A, then this whole region outside it, it will be A complement. And we know this is whole universal set. Then A union A complement, it will be completive. That is A. So A union A complement, it will be completive. Let us see second one, second property. The second property is A intersection A complement is equal to phi null set. Let us see it here. Let us say I have a set A, outside it will be its A complement. Now if I get intersection, I think we'll have no element common between A and its A complement. So we'll say that then A intersection A complement will be phi. Let us see the third property. The third property is based on De Morgan's law, and this is also called the De Morgan's law. The property says A union B whole complement is equal to A complement intersection B complement. Its second form is like this. It is its first form. Its second form is like this. A intersection B whole complement. It's equal to A complement union B complement. Let us see these De Morgan's law by the Venn diagram. Let us say I have a universal set. There are two subsets. Let us say it is A and let us say it is B. Now when we take A union B whole complement, let us say A union B whole complement. Since we know this is this region and this region, it will be A union B. These three regions will comprise A union B, and outside will be A union B whole complement. So it will be this region. So this outside region, outside these sets will be A union B whole complement. And we are seeing that it is equal to A complement. Let's find it here, A complement. We'll just make the diagram of right side on the next diagram, and let us check whether we'll get the same region or not. In A union B whole complement, we are getting the region outside the A and B sets. Let's find whether A complement intersection B complement is the same region or not. For that, let us make diagram here. Let us say it is A, it is B. We have to find A complement first because we need to find on the right side A complement intersection B complement. So A complement will be this region. Let us mark it with this. First, A complement will be all the region outside A, and this will be also A complement because it's outside A. Now let's mark the region B complement. Let's mark it with vertical lines. So B complement will be this whole region, outside region, and also B complement will be this region, outside B. Now if we see the intersection between these two complements, between the horizontal and vertical lines, we see that the intersection lies only outside AB. Here we have only horizontal lines, here we have only vertical lines. It means that they are not common, and we are seeing that the horizontal and vertical lines, they are coming in the region outside this. It means that this region is A complement intersection B complement, and that's the result we have proved, because A in the whole complement is this region also, and we are getting A complement intersection B complement also this region, so if they are equal. Similarly, we can prove the second part that says A intersection B whole complement is equal to A complement union B complement. So these are the Morgan's law. Let's move to the next one. Now the next is based on double complement. It says that A complement whole complement is equal to A back. Let us check it with a simple example. Let us say I have a universal set, let us say from 1 to 10. 1, 2, 3 up to 10. Let us say A is equal to, let us say 2, 5, 7, 9, 3. Now if I find A complement, simply it will be first 1, 2 is here, 5, then will be 3, it will be 4, it will be 6, it will be 8. No, 3 is already present. So 1, 4, 6, 8. Now if I find A complement whole complement, I have to take its complement. Already I know A complement is this. So it means A complement whole complement will be universal set minus A complement. So it means that then we'll have to subtract from universal set this whole set, A complement set. So I will get 2, then I will get 3, then I will get 4 is already present here, then we get 5, 6 is present, then we get 7, 8 is present, then we get 9. So I will get 2, 3, 5, 7, 9, 2, 3, 5, 7, 9. I can see that A and A complement whole complement are same. So this proves the property. The next property is based on empty laws and universal set. On empty set and universal set. The property says if I have a null set that has no element, that has no any element. If I take its complement, simply it will be universal. Similarly, if I see another, if I have a universal set complete in which there are all the elements. If I take its complement, similarly it will be nice null set. There will be no element. Let's move to some more results on it. Now, if I have seventh to sixth property. Now, if we have A subset equal to B, either A is subset or equal to B, then we will see that, then it implies that, it double implies that, then if and only if we will see that, then B complement will be subset or equal to A complement. Let us check it. Let us take A is subset B. For example, it's A and A is a subset of B. So let us take outside, we have B. So it is B. So A is subset of B. Now the property says then B complement. If I find B complement means outside region. It will be subset of A complement. If I find A complement will be this region and also this region. So I can see that the region A complement, it includes whole B complement. So I can say that then B complement is the subset of A complement because B complement is present in A complement. It contains, B complement contains all the elements of A complement. So B complement is simply subset of A complement. Let's move to next property. The next property is A minus B, it is equal to A intersection B complement. Let us check it. Let us say it is A, it is B. If I find A minus B, similarly, we know that A minus B is this region. It will be A minus B. Now we are seeing that it is equal to A intersection B complement. If I find B complement, in B complement, I can see this is the region, first outside region, and also the region, this region. Now their intersection is, if I see intersection, this region is the intersection. It implies that A minus is equal to A intersection B complement. Similarly, if I have B minus A, similarly, if I have B minus A, I can see it is equal to B intersection A complement. Similarly, now let's move to next property. Eighth property. The property is A minus B. It's equal to B complement minus A complement. Let's check it. Let's check it by Venn diagram. Let us say it's A, it's B. So A minus B, it will be this region. On the right, I have B complement. B complement will be this region. And also this region. A complement will be this region. First, this region, let us represent it with dots. This will be A complement, and also the outside region will be A complement. Now we are saying A minus B. A minus B is this region. It's A minus B. And if I see B complement minus, now B complement comprises this region and outside region. And A complement consists of this region and outside region. So when I subtract from B complement, since B complement has this region, and this region. When I subtract the A complement from it, in A complement, it has the only region that is common with B complement is this region. So when I subtract this one, I am left with just this one. So this is A minus B. So in this way, property is solved. The property is proved. So let's move to next one. The property it is based on simply distribution law. So we don't need to prove it. We can prove it by the same Venn diagram, but it's based on simply a distribution property. We can remember it. So the property says A minus B union C. It is equal to A minus B. Then we'll take union sign. For this union, I have to take intersection sign. Then it will be A minus C. Similarly, its second form will be A minus B intersection C. It's equal to first A minus B. For this intersection, we'll take union A minus C. Then we have A minus C. Let's prove it first one. Similarly, we can prove second one. Let's take the Venn diagram. In this diagram, we have three sets: A, B, and we have the third set C. Now, if I take A minus B union C, first let us find which is B union C. So, common region between B and C. I can see that between B and C, we have this region, and this region is also between B union C because it is a region that is common between all. So this is the B union C. These two parts will be union between B and C. Now if I find A minus B union C, A minus B union C, since I know A has this region, whole region, uh, and if I find A minus B union C, I can see that only this region lies in the region of A. So I am left with this region only. This one, and this part of A. Because this part is the common, so it will be cancelled. Because B union C is this part. Because from B union C, this part comes in A. So when I subtract A minus B union C, I am left with these three parts. One, this part, and this part. Now let us find the right side. First, I have to find A minus B. I know these two parts will form A minus B. Union A minus C. If I see A minus C, the region for A, but I have to subtract it. See A minus C. So I have to subtract C from it. If I subtract this C, I will get the region, these two regions. When I take their union, first I have these two regions and then these two regions. Then this region, and this region. When I take their union, I am getting this part that already I got from here. In this way, the property is proved. Similarly, we can prove the second property. So this was about the complement of a set. And in the next topic, we are going to do some more results and also the problems and also the cardinality of set. That is the last topic, cardinality of set, and also we'll prove some more results based on the operation that we already seen in this chapter.